we're given, for example, equation of the plane. We're given here 2x plus 4y plus 8z equal to 16. And from here we can find a normal to the plane. This is the coefficient of x, y, and z. This normal vector. Here it will be 2, 4, and 8. This is my normal. It's unique. There's only one normal vector to the given plane. But the points, we can have many points. For example, we want to find the point on a plane. The point on a plane, it must be satisfying the plane. So we take y equal to 0, z equal to 0. We get the value of x is x by 16 by 2 is 8. So 8, 0, 0. Or we can take x equal to 0, y equal to 0. We get here x equal to 0, y equal to z equal to 2. So 0, 0, 2. We can take here x equal to 0, z equal to 0, value y equal to 4. Get 0, 4, 2. Or we take x equal to 1, y equal to 1, 8, z equal to 16 minus 6 is equal to 10, z equal to 10 by 4, 8, we have 0, 0. And we can have many infinite number of points. In this way we can have on a plane. So second is the idea that we want to find the distance of a point from the plane. So it's always distance is a perpendicular distance. This is my h. So the formula for h is ax0 plus by0 plus cz0 plus d over a square plus b square plus c. I will explain you. Here we write the equation in standard form in this form, and then we substitute the value of x, y, and z. So I just take this one as a note 3. I have here a plane, and I'm given here in the plane, this is the distance p. We want to find the distance of this point from the plane. I can get here point p1, and I can join this point p1 and p. So I know second thing that we can find here normal to the plane. This is my vector normal to the plane. I denote this vector by n. Now if I find the component of p1p along vector n, so that will give me the distance h here. I draw perpendicular. That's my h. What's my h? My h is component of the vector p1p along vector n. So what's this one? This one is a p1p dot n. This is the idea. That's we can apply to find the component. This is my h because this is a perpendicular distance. So these two are equal. This is my h. So we say we can find h taking component of p1p along n. So similarly, we can have the case. We're having here node 2, node 3, we can have that we are given here two vectors. We have two planes, and these two planes are parallel. I want to find the distance between these two planes. That's not a difficult thing to do because we are having here this plane, and we are having here this plane, and we say these two planes are parallel. When these two planes are parallel, we have the normal vector. This is my n. I take a point here, p1 in the plane, and here point p in the plane. I can get this vector p1p. Again, what's my h? My h is the component of vector p1p along vector l. Same as I described here. Because they are parallel, so normal is same. We find the component of this one. This is my here, and this is my h. I can find by using this one. So that's my next question, which I'm going to solve, that how we can find the distance between two planes, or we can apply the formula to find the distance of a point from the plane. In this example, we want to find the distance from the point P, that's 1, minus 1, and 2, to the plane, that's 3x minus 7y plus z equal to 5, and we take 5 to the other side, that's equal to minus 5. Because we take the standard form of equation, when we find the equation of the plane, distance from the plane, we wrote this equal to ax plus by plus cz equal to 0. And our point given was point P, x0, y0, z0, and our formula which we derived was ax0 plus by0 plus cz0 plus d, and here we are having the coefficient a square plus b square plus c square. So we apply it, and we can get here this h is equal to, this is our point, this 3 into 1, this is x0, y0 is minus 1, minus 7 into minus 1, and plus z is 2, minus 5, we take the absolute value because we have the distance, divided by a square. A is our 3, 9, b square, b is our minus 7, square is 49, and c is 1, so get here plus 1. So we simplify this one, we can get here the result of this is equal to 7 over root of 59 unit, whatever the unit of length we are using, we can use it. So this must, we take the absolute because this must be positive. If not positive, then make it positive. So this was the idea for this example. We take another example. The next example is we want to show that this plane P1 and P2 are parallel. And if they are parallel, we want to find the distance, because we can find the distance between two planes only when they are parallel plane. When they are not parallel, then we can't find the distance. It will be changing. We don't have the fixed distance for them. When they are parallel, we can find the distance. So we given the two planes, we can find the normal vector to the planes. If the normal vectors are parallel, then the planes are parallel. So we can see it here that vector normal to plane P1 is our coefficient 4, -2, and 6. This is my n1. And vector normal to plane P2 is -6, 3, and -9. Now we know from our scalar that if we are having two vectors, when we have two vectors, they are parallel when we are having the ratio between the components are equal. That's vector A and B are parallel when we are having here. This vector A was having the components as A1, A2, and A3, and vector B was having the vector components B1, B2, and B3. We say these two vectors are parallel when the ratio is equal, or we say A is equal to some scalar time, the scalar multiple of each other, and even then we say they are parallel. Now we can see here the ratio of this one is 4 or -6, 2 or -3, 6 minus 4, this is -2/3. So we say n2 is equal to -2/3 n1. This implies that our vectors n1, here we say this is my n1, and n2, n1 is parallel to n2, and when they are parallel, this implies planes are parallel. Planes are parallel. When they are parallel, we can find the distance between two planes. One of the methods is that we used here, we take a point on a plane and then just find the distance by putting in this formula. Second is that we say, we take here the 2 points on a plane, and then we find here the scalar. We take here point P, small p1, this is my point, says Q, and this point is R. And I get here vector between these two planes is QR. Now this is my N, this is my N1, and they are same. So I can find the component of this one about vector N. So this is my H. My H will be equal to component of vector QR along vector N, N1 or N2, because they are both are parallel, we can take it. So that's the idea we use, and we solve it. So I need the points on a plane. So I take as I explained you before, I take a point on plane P1. So that point on plane P1, point on plane P1, we take x equal to 0, y equal to 0. What's my z? Z is equal to 1/2. So this is point on point R on P1. Then I can take here the point, this point is point R. So this point is point R on plane P1. So I can just write it here. This is my R. So I take another point on plane P2. So here is P1. Then it's my I take this point Q. So I take the value of x equal to 0, y equal to 0. I get here 0, 0, and get here -4/9. So this is my point. So I can find here the vector QR. Vector QR is equal to 0 minus 0 is 0, 0 minus 0 is 0. And then here is RQ. This here is 1/2 plus 4/9. So this is 17 upon 18. So we can find here the component of vector QR along vector N is equal to QR dot vector N, or magnitude of vector N. This is my N1. So we can have here the dot product of these two. So multiply, this will be 0, this will be 0, is 17 by 18 multiplied with 6 is 17/3. And over is we having the under root of, this is 16 plus 4 plus 36. So I get here 17/3 into root of 56. That's my distance between these two vectors, between two planes, I denote by h, and this is my here in the units, whatever I get. I have here the plane P1, and I have the vector N1 to plane P1, and we're having this plane P2, and I have here point on plane P2, and this point was point Q. If we are not wrong, this is plane Q, and the point Q was here 0, 0 minus 4/9, and the equation of the plane was here 4x minus 2y plus 6z minus 3 equal to 0. Now I will use the same formula as I did in the last example. My h is equal to a x0 plus b y0 plus c z0 plus d over we are having here a square plus b square plus c square. Now I substitute the value of my a0 is given to me, that is here I can find now this distance is my distance h, and this is equal to ax0 is equal to 0 plus 0 plus we are having here minus 4 by so 4 by 9, so it's minus 4 by 9 into 6 minus 4 by 9, and then we're having here the value is 6z into 6, and this minus is minus 3 over root of, we can have here the a square plus b square plus c square, 16 plus 4 plus 36. We simplify this one, we get here this is minus cancel 3 minus 8 upon 3. We're having here minus 8 upon 3 minus 3 is absolute value over we having here 56, and we simplify this one, we can get here the value is result is equal to this 9 is minus 17 into 3 over 56. The same result which we solve by the method, the 17 over minus 3 over 56 is the idea that we can, this is second solution, a second way of solving it. I will write here second solution, and this was the first solution where we use this formula that our h is equal to, where we use the formula that our h is equal to the component of pq, and we find vector pr, we find n1, and we apply it here. We prove that these two planes are parallel. We can find the distance between the two planes when they are parallel. Where how can find the parallel? We get the normal vectors and then take the ratio of normal vector, or we say one normal vector is scalar multiple of the other, so they say they are parallel.